Tutorial on AI in biomedical research, bridging data, causality, and clinical impact. And the presentation will be from Judith Abecassis from INRIA.
Hi everyone, so thank you so much to the organizers for having me here, and don't hesitate to interrupt if you have any questions during the presentation. So I'm going to show you a few insights about how to make AI slightly more useful than if you do it completely naively. So of course I'm going to present you how and explain to you how much improvement we have seen in AI models. But a real game-changing in biomedical research now is the amount of data that is available with claims data from insurance and reimbursement, tracking all your medical events. Also, hospitals holding electronic health records, and of course, all the data that is produced for research and stored in many databases that are reaching millions of individuals. So there is a big hope now of how we can leverage all of this data and state-of-the-art models to just advance knowledge and science. And it's not that easy. So if we just go to what most models of AI are, I'm mostly going to focus on supervised learning. So supervised models are really useful for a lot of things. So if we just have data with labels and we try to predict the labels on new similar data, so it can help forecasting the weather and maybe also hospital demands or drug demands to try to keep up with what will be needed. We can also focus on stratifying patients to focus resources on patients that would need it the most. We can also try to discover some markers for clinical progressions or improve diagnosis. We can also automatize a lot of background tasks, both in research and in healthcare, to try to save more brain time to do interesting things like workshops. And but we should be really, really careful about how we use those models and what we learn from it. So a predictive model, we usually try to assess their performances. So if I go to standard classification, we mostly have implemented pipelines where we can just run a few lines of code to get a full benchmark, trying several models, even neural networks very easily, and cross-validation, hyperparameter optimizations with the area under the ROC curve. So it's one metric that is really interesting, and that focuses on if a model is able to discriminate between two classes. So that's the one cases where we are happy to have a good discrimination. So, but we could also focus on other aspects of how the model works that can be really important when coming to support clinical decision. And one of those metrics would be calibration. That is, not focusing just on the predicted class, 0 or 1, but also to the probability with which this model is predicting. And it can be important in how you receive the news. So you have 70% chance to have this or this outcome. You would be unhappy if this 70% is completely off. And so calibration mostly compares the predicted probability to the true probability. But another very important aspect of those metrics, and if you look at classification metrics, there are dozens of them, but you should absolutely try to focus the one you use to your use. So here is one metric that is specifically designed to assess the clinical utility, which is called the net benefit. it's not used a lot in standard machine learning, so it's not very original. It just includes some things about the true positives, the false positives, and some ratio between the two that actually reflect the threshold probability that you are going to set, and it mostly reflects how many false positives you are willing to accept to get a true positive. So if you just want to propose an advanced screening for cancer, you should you are prepared to offer it to a lot of people, not to miss any case. But if you just want some alarms in the ER, you don't want every machine beeping every other 5 seconds. So so you should really think about what you want to achieve. And depending, so here are different models with different performances. So you see that the more, of course, the more performing you are, the more useful you are, but it's not completely equivalent. So another very important aspect of evaluation is, of course, generalization to other data. So if you are just in machine learning, usually you have your data set, you split it into train and test. You may use cross-validation to assess the best hyperparameters before looking at the test set. And if you are actually trying to apply it, you should also focus on generalization. So will it work the same in slightly different environment or not? And that's so you can assess it with different data sets coming from other sources, like a different hospital, a different country. And the hope is that the better you generalize, the most the more you are relying for prediction on important things and not just data leakage or artifact. So we are going to go back to some interpretation about that, but this notion of generalization and external validity is actually really tied to causality. So now if you look at real case of predictions of such models, so this is an example, so it's a little old now, but it would work probably the same. So it's image recognition and pattern recognition images, and here you see that your super neural network is actually recognizing a cow in its natural environment of mountains. But if you have a similar animal on a beach, which is less frequent in some data sets, it actually completely fails to recognize a cow. And you can have several examples of such cases showing that it's not just bad luck. So what's happening here? Probably the prediction and the recognition of the cow is not relying on the cow characteristics. So we see that the presence of the cow and how the algorithm works is associational and not causal. So you can have other examples. Here is an example of prediction of pneumothorax, which is when your lung collapses, basically, based on X-ray. And if the developers of the model actually analyzed it and what was actually predictive, and they found that it was the presence of a drain to try to take the fluid. So after a doctor, so basically what happened is that the doctor could diagnose a pneumothorax based on a clinical exam before and actually put some drain in the patient that needed it before sending them to radiology. So then the data sets collected to train the algorithm was a little flawed and not reflecting when the doctor was actually needing it for diagnosis. So again, the algorithm and the predictive algorithm is not learning what we would like it to learn, which is to recognize a lung with a pneumothorax. So But actually, all those predictive models can be quite useful. So here is an example of projections about ICU bed occupation in France during the COVID crisis. And if you just want to know what is going to happen and what you have to expect, using such a predictive model is useful. What you shouldn't do is try to then assess whether what would change if you would change one of the parameters. Then you are slipping to causation and to causality, and we are going to see when and how you can do it. So you have to be extremely careful, and I just fall for it every other week, because when you have a predictive model and you find some variables that are really interesting and really correlated to what you want, and what you are caring for, you are actually really tempted to say, oh, okay, so if you hear the most correlated variable and the most important variable in the model is weight, it's really tempting to say, oh, okay, so if you lose weight, or if you maybe gain weight in some cases, then you are going to see a change, but you don't have actually any guarantees from your predictive model. So how to obtain them? So we have to be really aware and self-aware that a predictive variable is not a causal variable. So the prediction is what is the outcome for some combination of the parameters and the variables in the reality. And causation or intervention, I'm going to mix a little the two, even if they are not exactly the same, would be how is the outcome that I'm targeting for going to change for a different value of one of the predictive variables. So again, it has many applications that are a little different from the predictive model. So we can focus on the effect of a treatment or an intervention, of a marketing campaign, of a public policy. And the good news is that we have good principles to make sure we can measure those. So now coming to how we are going to mathematically distinguish those causal problems from predictive problems. So we are going to live in the potential outcomes framework. There are other causality frameworks that I'm not going to show today. So we are considering T, the treatment or exposure, because sometimes it can be harmful. The covariates, that are the features describing each unit. And we have Y, our usual target variable that we called outcome, which is observed. And we are going to consider some variables that are unobserved, that are the potential outcomes, that are what would happen to the unit with a different value of the treatment. Then we can very easily define what is causal, and what is the effect of the cause, and it's the difference between the two potential outcomes. But comes the fundamental problem of causal inference, which is we never observe both. I'm saying both because we focus on the binary treatment, but we could consider more than two, both potential outcomes at the same time. So if we observe them, we could just consider this difference and try to predict that with a predictive model. It would be fine, but we never measure those. So how are we going to do? We are going to try to focus on something that we could estimate, which is the same, but at the population level. At the individual level, it's hopeless. But we can try to see what happens on average between the potential outcome with the treatment and the potential outcome without the treatment, which is the average treatment effect. And we are also very interested into the conditional average treatment effect. So it's still an expectation, so broadly an average on the population. It's still not an individual effect, but we can think of it as an individualized effect where we try to see what is the effect with some characteristics to try to approach what can happen to one particular individual. So now those estimates, as you see, they are expressed in terms of potential outcomes, with missing parentheses. So we actually can't estimate them yet from our observed data. We need one more step, which is identifiability. So we have defined both of them. So yeah, just a little note about the conditional treatment effect. It allows us to consider the heterogeneity of a treatment effect and then go towards personalized treatment to actually focus on the patients that would benefit most from the treatment or the intervention. So now for identification, to go from those unobserved variables to something that we can actually estimate from the observed world, we need additional assumptions. So the first one is consistency. It's also called SUDVA, so Stable Unit Treatment Value Assumption. And it's very tautological when we just look at it this way. It would be the potential outcome plus the, so yeah, so basically it states, if you look at different values for T, that it's the potential outcome without the treatment if the unit doesn't have the treatment, and the potential outcome with the treatment if the unit has the treatment. So it really relates and links together the potential outcomes and the observed outcomes. Otherwise, there is no guarantee that they are linked together. So it's actually weird to think about it that way, but if we look at additional formulations of it, one aspect of consistency is that we have one single version of the treatment. Otherwise, we would compare different things for different units, and it wouldn't make sense. And we have no interaction between the units. That means that the outcome that is going to happen to a unit is linked to the treatment received by this unit and not by other factors in the environment. Otherwise, we wouldn't have a single effect defined well for one unit. So it's important for each problem to discuss how plausible this assumption is, and actually in very familiar situations, it's not at all plausible. So if you remember, for a few years back when we had to wear masks, there was a clear definition of how we should wear a mask. It was above the nose and below the chin, otherwise some air could spin through, and it's actually not the same effect at all. So if we just say, okay, you have to wear a mask, it won't have the same effect if you wear it incorrectly. And in the case of these infectious diseases, and it's also the case for a lot of vaccination analysis, actually your risk, your individual risk, depends on whether the other people and the other units are having the treatment. So if you don't wear a mask, but everyone wears one, actually you have the same outcome as if you were wearing a mask, more or less. So here it's one case of breach of those assumptions. So actually you see that a lot of interesting situations don't go into this framework, but there are some additional mass to compensate for it. So remember, just one single version of the treatment and no interaction between the units. So now there are two additional assumptions that we are going to see in the case of a randomized experiment. So in a randomized experiment, usually it's the ideal case when we want to have causality, and so that's what pharmaceutical companies and doctors and publicists do to try to assess how it works. So we have two assumptions. The first one is positivity, that every unit is, has a non-zero probability to get either version of the treatment, and ignorability. So it's not that the outcome is independent of the treatment, that would be not what we are aiming for, but the potential outcomes are independent of the treatment assignment. Okay, so what would happen to a unit in either case doesn't guide who is going to get or not the treatment or the intervention. So with those two assumptions and very simple algebra, we can actually see and obtain an equality between the expectation of a potential outcome and the expectation of the observed outcome in the treated group. And we can do the same for the potential outcome under control, and we end up with the average treatment effect in that case being that can be estimated by just looking at the difference between what happens in the treated group minus what happens in the control group. So we simply compared both groups with different versions of the treatments. So if the treatment is randomized, we can do that. But in a lot of cases, we can't randomize the treatment, so it can happen for ethical reasons. Like if we suspect that the treatment is dangerous, we can't ethically force some people to have it. And in some cases, it can also take a long time, so not completely compatible with the experiment, and it can just be a matter of cost. So, if you remember, we can't always randomize the treatment, but we are sitting on a lot of data, so maybe we can use those, and so we can have slightly relaxed versions of our identifiability assumptions to go back and try to do something with observational data. So instead of positivity, we now have conditional positivity. So every unit is susceptible to get the treatment, conditional on their features. So for any unit with any characteristic, they should have both versions of the treatment possible. So it means that the intervention is not deterministic. And it's absolutely necessary if you go back to a more intuitive interpretation. We are, in the randomized case, we are comparing the treated and the untreated. So here we are sort of aiming back to that situation conditionally on the covariates, and so we want to have a unit with comparable features in the other treatment group to make the comparison. If we have no one, for example, if in one group we only have women and in the other group we only have men, then we can't really compare what happens with sport or with smoking, because we won't know if it's the effect of our intervention or of other characteristics that we are observing. Okay, so we just have to make things comparable. Some math can fix imbalance between the two groups, but up to a point. The second assumption is conditional ignorability or conditional unconfoundedness. So again, we have that the potential outcomes are independent of the treatment assignment. Again, conditional on the covariates. So intuitively, it means that any factor that would break this independence assumption is adjusted for. There are no unmeasured confounder. There can be some factors influencing both the treatment and the potential outcome, but we should measure them and adjust for them. So the big problem with this is that it's untestable. So we will go back to how we make it plausible. So of course it's true if the treatment is randomized, but it's not always the case. So just a little toy example to show you how it works in practice. So it's COVID again, because it's the time where we all became epidemiologists. So if we were to compare and to try to assess the effect of vaccination, even though it's not completely okay with the first assumption. A naive way would be to compare the number of deaths and the death rate in the group that is vaccinated, which is the darker ones, and the group that is unvaccinated, that is the lighter ones. And if we strictly compare, we could find that actually there is a higher death rate in the group that is vaccinated, because there is a lot of death in the more aged group. So now, if we additionally break the data and stratify the data by age and separate moderately young people and not as young people, we find that in both those subgroups, there is a higher death rate in the unvaccinated. So here there are not so many people, but 40% of death against 13% in the vaccinated group, and the same for younger groups. So actually, we observed a higher death rate in the vaccinated group because, in proportion, it's mostly composed of older people. Okay? So we see a higher death rate in this vaccinated group because it's in composition, it's composed of older people than in this other group that, although unvaccinated and more subject to severe COVID, was young and protected by their age. So we see that here. So it's an example of the Simpson paradox that is that you may have heard of, or you will hear of it again. And so here you see that just adjusting for the age, which is the covariate of interest here, helps correct for that. So now if we go back to our estimate of interest, which is the average treatment effect, we can actually use all our assumptions. So first, ignorability and positivity to condition on the covariate and the received treatment, and then consistency to have this link between the potential outcome in the right group of intervention, and we end up with conditional expectations that we only depend on observed covariate that we are now going to see how to estimate. So we have reached our first objective, which is to express our estimate, the average treatment effect, with only observed variables at the price, the very high price of very, very strong assumptions. So now, how can we make sure and discuss the plausibility of those assumptions? So I'm just going to introduce you a tool, which is the causal graph. So it's actually a very developed alternative theory in causality and causal inference. So I'm not going to go into details, but the way I use graphs is to actually state what we believe about one problem. So how do we obtain those causal graphs? Either we build them using expert knowledge, or there are also techniques to build them from the data. So I'm not going to focus on that. I'm just going to assume that I have access to a particular graph, or maybe a family of graphs if there are alternative and uncertain parts of the graph. So what is it? It's a mathematical object where I represent all the variables that I consider interesting and important as nodes in the graph. The edges are oriented and reflect some causal relationships between the variables. So actually, if I'm not sure about what is happening, for example, I don't know what this x1 variable is doing, I should put edges towards all the other nodes. The big assumption is not in the absence of an edge, because that's where I say, okay, I believe that this variable is actually not influencing at all this other one in a causal way. And there should be no cycles, because otherwise the problem is intractable. So now if I have such a graph, there are a lot of rules that you can use to actually assess if you have identifiability or not based on the graph, but mostly the structure of the graph is going to distinguish and define different groups of variables. So the ones that we have discussed before, the confounders that you have to adjust on, that are like the age in this COVID vaccine example. So, but actually, the graph allows you to visualize some other possible relationships, like a mediator that would be an intermediate explanation of your sort of step in your causal effect. So, for example, maybe you could consider that your COVID vaccine is making you having a high level of specific antibodies to COVID. So this antibody specific would be a quantity would be a mediator. And there are also colliders that would be common consequences of the treatment and the outcome. So I'm not going to go into more details, but the important thing is that you have to adjust on the confounders, and you have to absolutely not adjust on the mediator and the collider. So laying everything on the graph may help you refrain from adjusting on mediators and colliders. That would create a bias in your estimation. And it can also help you spot that there are some variables that you would find important, and that could be potential confounders that are unobserved. So once you have a graph with all those groups of variables, it's sort of straightforward to pick an adjustment set for your problem, and also to reach the conclusion that maybe your problem is not identifiable because you have too many unobserved confounders. But of course, in real life, things look a little more complicated than that. So here is a sort of over exaggerated example, but you know, this one that I had here is also quite simplified causal graph, and you see that it's already getting complicated and it's already hard to follow all the edges and paths in the graph. So it's a good way to represent all the assumptions that you are making, that you would never write in the text extensively, but it remains complicated. So now, once you have reached a state where you believe that your assumptions are plausible, where you can make a good argument that you observe the main confounders, that you can say that although you try to adjust for as many variables as possible, you were careful to exclude some variables that you are not supposed to adjust on, you should go forward with estimation.
Could I ask what you mean by adjustment? Sorry, it's probably obvious, but...
So adjustment would be sort of the same as conditioning, okay, in the way that you are defining the assumptions. And actually, mathematically, there are several ways to adjust for covariates, which is basically the main strategies for estimation that I'm going to present right now. But if you are very in a very simple way, adjustment is conditioning. So usually you condition on particular variables on particular values of your covariates, and that would be equivalent to making subgroups. Of course, as your number of variables is increasing, you can't really make subgroups. You are losing your statistical power. So that's where those estimation strategies just come in. That's a very good question, and actually the core of what is going to happen. So a first way to adjust is to try to actually, so the main problem that we have in observational data is actually that we have a shift of covariate distributions between the treated group and the control group. So if you compare people that go to hospital or not, of course the ones that go to hospital are not comparable to the ones that don't go. They are usually sicker. So the ones that get vaccinated are older and so on. So you actually want to compensate for this covariate shift distribution to make the groups comparable and try to go back to the randomized situation. So one way to do it is to reweight the units in your two populations to actually make the distributions of your covariate match. So one easy way to do it is to adjust with the inverse of your propensity score, the propensity score being the probability to receive the treatment based on the covariates. So you want to estimate the probability to get the treatment depending on the covariates values. So it looks a little weird, but it's actually what you can estimate using a classification problem in machine learning. So either with a simple logistic regression, so a linear model, or more complex machine learning models. And once you have estimated those propensity score, you can simply reweight its units depending on their probability to receive the treatment, and basically compare the average of your outcome in the treated group and in your control group with this reweighting. So visually, you can imagine having the value of your outcome depending on the covariates. And what you see is that in some regions of the covariate space, you have much more units of one group compared to the other one. And so what this does is actually to reweight the units that are underrepresented so that you sort of have equal weight of the two groups across the full covariate space. So that's one way to do it. And of course, you may see that and think about the fact that we are dividing by probabilities, and that can lead to instabilities if you have very, very high or very, very low probabilities in some parts of the covariate space. So that's the mathematical view of the positivity assumption. So that's why we assume that every unit across the covariate space can get the treatment. So here in this graph, you actually see that here you have only units that are in the control group, so there might be a slight violation of this. So because of this instability of estimation, and also because people have imagined a lot of ways to actually adjust for covariates, another way is to, and another strategy for estimation, as your statistical estimate is just a conditional outcome that you have identified as the, so if we go back to identification, we just saw it was the expectation of the observed outcome in the treated group and in the control group based on covariates. And so this looks like it, and this is actually what you can estimate with regression. So instead of trying to readjust the weights to make both groups comparable, you can just focus on the covariate distribution and try to predict what would happen with the other version of the treatment, so make a sort of counterfactual prediction. And so once you have a model for your outcome with different values of the treatment, you can simply plug them in your initial estimate and compare what happens with the treatment and without the treatment for different values of the covariates, and so different sorts of individuals. Okay, so this is what is represented here. You can imagine having some units that are treated or untreated, and you can try to predict and estimate what would happen in the other situation and consider the difference between the two as the treatment effect. So what is really nice with this estimation strategy is that you directly estimate the conditional average treatment effect. So you are in the situation where you can try to personalize the treatment effect prediction. But so it seems that you are better with this positivity assumption and the fact that you have some imbalances of representation in different parts of the covariate space. But because you are not dividing, you are not having any numerical instability. But actually, if you go a little deeper into what happens in those situations is that you are making some extrapolations. Okay, so you actually compensate by having a prior about how your potential outcomes models are looking into spaces that you don't observe or that you barely observe due to a low frequency. So some people had the idea to combine those two approaches to try to make the most of them. Also, a problem that I did not mention is that in both strategies, you are modeling something. So you are making an intermediate model, which is either linear, which may not reflect reality, or that can be badly estimated with more complex models. So, so either the propensity score model, which is a classification problem, or surface responses in the case of regression-based approaches, and they are subject to misspecification. So an idea would be to combine both those approaches to try to have a compensation between their strengths and their weaknesses. And so the main idea is to actually do both, and so to make both groups more similar before applying a regression estimation and to end up with a less biased model. So what you obtain then is called the augmented, or one example of it is the augmented inverse propensity weighting, where you estimate both surface responses and propensity scores, and you combine them with this slightly complicated formula where you can actually rearrange the terms. So either by having a first part that is exactly your plug-in regression model and a term that is actually going to cancel out if that is going to actually cancel out. So if your regression model is well estimated, this part is well estimated and consistent. And as you have very small differences between your model and your real observed outcome, actually the part that depends on your propensity scores doesn't really account and doesn't really lead to an error. And you can also rewrite it so that you make the inverse propensity score weighting estimator appear. That is going to be consistent if your propensity score is well estimated. And you see that those terms are going to be close to zero if it's well estimated. And so even if you have a very bad model for your potential outcomes, it's your overall estimator is going to be consistent. So there are also other ways to rewrite things along and combine both ideas. So based on the Robinson decomposition. So here again we define our outcome depending on the covariates. And we can actually rewrite it so that we make appear the treatment effect. And so by rearranging those terms, we can then have actually an optimization method that directly tries to optimize the treatment effect that leads to the smallest estimation error compared to the observed data. So that is leading to another model called the R learner. So I'm not going to go into more details, but what we end up here as a situation is that we have many options to estimate the same thing. And we have an additional level of diversity, which is the choice of the machine learning model or the regression model or the classification model that we can plug in those estimators, which may lead to different results. So here we have two models, or actually three. We have put for the X learner and the R learner. So the R learner that I presented and the X learner that is also another combination of reweighting, and so it's really exactly the same ideas. And we see that depending on which underlying model, we end up with biased or not biased estimations of our true causal effect, which is the blue line. So we see that the S learner, which is a very simple model with a linear regression, is completely failing to capture some aspects of the treatment effect. And here we have a slightly weird, not smooth effect that is not well captured with linear models. But we actually see that more complex models, like gradient boosting trees, also don't capture this subtle effect here. A reason for that is that we will have very few individuals in this covariate space with very old people. And there is some limit to what machine learning and causal inference can do with the data. So now that we have all these toolbox to conduct and very complex estimation, is having all those very complex models and found the right adjustment set in terms of covariates enough to obtain well-principled causal effects estimations. So I'm going to show you two real-life examples. So the objective is absolutely not to point fingers, because it's actually a very, very difficult problem, and I'm always the first one to be really tempted to just say, okay, my data is pointing to this very, very big revolution. But we have to be really careful. So the first one is about the prevention of cardiovascular events in the UK, but also applied elsewhere, of course. So in the UK, so they have designed a score, a risk score that is called the Q-risk, that is very well principled. It's more a predictive model to assess whether you are likely to have a cardiovascular event within 10 years or not, and actually it's well calibrated. It has a good clinical utility. Everything was done by the book, and there are some results from meta-analysis, so combining a lot of randomized clinical trials that suggest that using statins as in primary prevention, so in people who never had any cardiac events, had a positive effect in preventing further cardiovascular events. And in real-life application of this score and this principle of prescribing statins, no result was seen in real life, and there have been since some additional meta-analyses that have analyzed this effect of statins on cardiovascular prevention, but additionally to stratify on age and sex, as was done before, they also stratified on this cure risk score. So they compared the effect of prevention among people that had a high risk to develop a cardiovascular event or a low risk of developing cardiovascular events. And there, in the meta-analysis, they found no effect of the statins, because actually there must have been some imbalance in the previous studies in terms of representing people with high risk or low risk in the treatment and control groups of the different models. And in addition to this problem, which was a bad adjustment effect, actually the meta-analysis pulled together cases with for primary prevention, so when people had no experience before any cardiovascular event, or secondary prevention, when they had experienced some small cardiovascular events and were trying to correct cardiac problems and underlying disease with statins. So another component of a valid analysis, so here it's focused on healthcare and biomedical, but you can have it in any field of science. You have to actually really define what you are considering, in which population, in which adjustment. So there are some guidelines in the healthcare framework, so either the PICO framework to focus on defining well your population, what is your intervention, what is your control population, what is the outcome that you are considering, and it's also really close to the target trial emulation framework that is very famous too. So another example of, it's a little cut, of this is the case for use of aspirin to prevent cancer relapse. So there has been, again, some encouraging results from observational meta-analysis, so trying to go back to and to pull together meta-analysis. So for example, this one that I cite here, I should correct that in the final version, looked at almost 1 million patients with breast cancer and found some positive effect of aspirin in this retrospective analysis. There are also some hypotheses about how it would work, because aspirin is suspected of reducing inflammation, which is then involved in breast cancer relapse and other cancers. And it was so compelling that an RCT, so a randomized control trial, was started to analyze this effect of aspirin on breast cancer relapse, and 3,000 patients were enrolled, and the trial was actually stopped early because at an intermediary point, no significant positive effect was found in this case. So retrospectively, going back to the initial meta-analysis, we can find several issues, like no well-defined dose of aspirin to be followed. So again, breaching this first assumption that I mentioned, and also the initial some clinical parameters were not fully adjusted. So we can imagine that all both those examples were really reviewed by a lot of very eminent people, and the conclusion of that is that it's actually a very, very big and difficult problem to have all the steps right to conduct a clinical analysis. So we should first very carefully design the causal question, and there might be also differences and a lot of choices made in how you prepare and treat the data, and the missing values and the noise in the data, the errors. Then you have a lot to think about at the identification step, and what prior knowledge and what causal assumptions you put in the graph and in the choice of covariates to adjust. Then you have to conduct estimation, and so I didn't go into details, but you also may try different models, and if they yield very, very different results, you should go back and dig into your data to see what is going on. So a lot of steps, a lot of choices. In the end, a little machine learning just at this step, but a lot of the other steps is actually common sense, discussing hypotheses and making analysis choices. So thank you. Oh yes, so in maybe a concluding word. So very briefly, actually, even if you don't try to do causal inference, having those notions of confounders and selection bias in the way your sample was collected, in the way you eliminate or not observations with missing data, are really useful tools to refrain from jumping to causal conclusions, like A is correlated to B, maybe acting on A would be a good idea to change B. So causality from observational data will always be imperfect, no matter how hard we try to adjust on covariates and define things very precisely. But going all those steps and all this sort of very big checklist is actually helping us towards the right direction. And so, of course, there are a lot of room to develop new methods, to relax the identifiability assumptions and develop better algorithms and have better ways and safer ways to use complex machine learning models. And so, of course, use causal reasoning carefully, but systematically when you analyze and interpret your models. And you should do it in collaboration with expert domains, because no matter how hard we try, we always miss some things. So yeah, thank you for your attention, and don't hesitate if you have questions.
Thank you very much. We have some time for a few questions. Yes.
Hi, thank you for the talk. So regarding the adjustments for this covariance between test group and control group, how do we know if we are using sufficient amount of covariance to do the adjustment? So for example, if there's some unobserved covariance that really heavily affects everything, can we check, or can we
No, we can't check. So one check we can do is after you train the propensity score models, if you adjust and you reweight your units for it, we can check all the other covariates and check if they are now balanced in this reweighted version. So if they are not, there is some issue. If they are, it's not a guarantee that you have adjusted enough, but it's a good sign. And of course, the main limit of what we can adjust for is the current state of the knowledge. So we can always hypothesize that there is some factor that no one knows about that we haven't adjusted for. So we can never know for sure, but first this little mathematical check, and then trying to look through the literature or experts to have some other ideas might help, but we are never sure.
More questions? Online, maybe? Questions? I would have a question. The examples you gave towards the end of the presentation, yes, of meta-analyses where there was a confounding effect which wasn't identified, and whether is that something you were able to discover using the causal discovery methodology, or is that something that?
So in both those cases, there was an initial meta-analysis and then a further meta-analysis that would adjust for more variables and not so complicated ones, but and found different conclusions.
Okay.
But yeah, I don't know from the top of my head of any causal discovery new adjustment. The big difficulty of causal discovery is that you actually have to include those additional variables in the set you are looking at, so which is, you have to think about them and have measured them in a significant amount of of observations beforehand. So it doesn't help with these things we don't know.
Mm-hmm.
Maybe a step a bit aside. So if we use causality to interpret, or to try to interpret, it says neural networks, prediction models we use, like with counterfactuals. So then we are using causality just from observational data or context, but we can intervene, right? So you want to do some explainability with a model that is pre-trained, okay. But then now you have possibility to intervene, right? Can you comment on that?
Yes, so there are some causal discoveries approaches that try to combine observational and intervention results, in particular with all those high-dimensional causal gene-gene interactions or things like that. So basically what you can do is check that your assumed graph will behave the way it should according to your intervention, but check that your intervention results are compatible with your graph. So yes, but basically that's what most causal discovery methods do. They check a lot of assumptions, and like for example conditional independencies, and then they see if they are compatible with the data. So of course if you have intervention data that are more robust, and they should help, but the bigger your graph, the more you should have. But that's definitely a very promising way to combine observational and interventions.
There are no more questions. Let's thank the speaker again. Thank you very much.